Hey everyone! In this section we're going to be learning about the normal approximation to the binomial probability distribution. So remember we learned about a binomial probability distribution in experiments? Let's go through that again real quick. A probability experiment is considered a binomial experiment if the following are true. Number one, the experiment is performed n independent times. These times are called trials. And independence means that the outcome of one trial won't affect the outcome of other trials. Number two, for each trial there's two mutually exclusive outcomes, either success or failure. And then number three, the probability of success, P, is the same for each trial in the experiment. So if all three things are true here, we call that a binomial experiment. So for a fixed P, remember P is the probability of success, as the number of trials n increases, so the more trials we do, the probability distribution of the random variable becomes nearly symmetric and bell-shaped. So the more trials we do, this binomial distribution, probability distribution, starts to look like our normal distribution, symmetric and bell-shaped. So as a rule of thumb, if we compute n, number of trials, times p, our probability of success, times the probability of failure, which is 1 minus p, if that number is greater than or equal to 10, then we say that the probability distribution will be approximately symmetric and bell-shaped. So the normal approximation to the binomial probability distribution, so this is just reiterating what we just said. If this calculation is greater than or equal to 10, then our binomial random variable is approximately normally distributed. And then our mean, mu sub x, is just n times p, and the standard deviation, sigma sub x, is square root n times p times 1 minus p. So this graph right here shows the probability distribution of the binomial random variable x when n is 40 and p is 0.5. So 40 trials, probability of success was 50%. And so if we plug in n and p into our calculation here, we end up with exactly 10. And so as long as it's 10 or more, we can say that it's normally distributed. And so we can go ahead and use our normal model. And then to calculate mu, we do n times p. In this case, we get 20. And our standard deviation, sigma, we end up getting 10, square root 10. So to approximate the probability of a specific value of the binomial random variable, like let's say we want to calculate the probability of 18, what we actually do is we find the area under the normal curve around 18. So we would say from x equals 17.5 to 18.5. So we add and subtract 0.5 from our x value as a correction for continuity, because we're using a continuous density function to approximate the probability of our discrete random variable. So if you recall how this went before, when we talked about this in the past, if you want an exact value for x in that probability, it would technically be 0 because we're using area. So it would be like a rectangle with a width of 0. And so what you do is you actually just kind of give a little space to the left and the right of this number, therefore creating a width for your rectangle to find the area under your curve. And so to approximate the probability that x is less than or equal to 18, we actually just add 0.5 to that, and we say we're looking for the area under the curve for x less than or equal to 18.5. If we want to approximate probability that x is greater than or equal to 18, we look for 0.5 less than that, so we say greater than or equal to 17.5. And so here's a table for just 4 different situations. If you want to compute the probability of an exact value for x, what we actually do to approximate it using the normal distribution is we add 0.5 and subtract 0.5 from those numbers, or from that number. And here's the diagram to show you what I was just saying about the width of a rectangle. This now creates a rectangle with a width, and so we can calculate width times height to get the area, and that gives us our probability. If we want a probability of x is less than a number, less than or equal to, we add 0.5 to that number. If we want probability that x is greater than a number, we subtract 0.5 from that number. And if we want the probability that x is between two values, we subtract 0.5 from the smaller number and we add 0.5 to the bigger number and compute that probability. In other words, that area between those numbers. So taking a look at our example here, according to the Red Cross, 7% of people in the United States have blood type O negative. What's the probability that in a simple random sample of 500 people, fewer than 30 have blood type O negative? So first, let's verify that this is in fact a binomial experiment. So each of these 500 independent trials won't affect each other, and they all have the same probability of success, 0.07, and there's only success is they have the blood type, and failure, they don't have the blood type. Those are the only outcomes. So this is a binomial experiment. So next, let's verify that this computational value is greater than or equal to 10. That will tell us if we can use our normal approximation. So we plug in our sample size n, 500, our probability, 7%, and then the complement of that is 1 minus 0.07, which is 0.93, or 93%. So we get 32.55, which is definitely greater than or equal to 10. And so that tells us that we can use a normal distribution to approximate the binomial distribution. So then we can move on and say that the probability that fewer than 30 people in the sample have blood type O negative is P probability of x is less than 30, which we're going to actually say that that's probability that x is less than or equal to 29. And here, so we just changed it because if we want fewer than 30, we don't actually want 30. We want 29 or less. And so this is approximately equal to the area under our normal curve. So we verify that we can use our normal distribution here for approximation. So this is approximately equal to the area under our normal curve to the left of x equals 29.5. So we added that little 0.5 that we were talking about. And so we have our mean by just saying n times p, that's going to be 35. Our standard deviation is going to be 5.71. And then let's take a look at that. So here is our normal distribution. So our normal curve, our mean is right here in the middle. Our 29.5 value, we wanted numbers less than or equal to that. So we want the area under the curve less for any part less than or equal to 29.5. And so we can get this number by finding the z-score. So first you're going to take, we've talked about this before, but you're going to take your x value and you're going to convert it to a z-score by using this calculation. So this calculation is going to be your x number minus your mean over your standard deviation. We've used this in the past, but if you need to write that down, this is x minus mu over sigma. That gives us negative 0.96. And then you go to your table for standard normal distribution. You can find online or in a textbook. And then for a z-score of negative 0.96, we get that the area to the left under the curve is 0.1685. So there's the approximate probability that fewer than 30 people will have blood type O negative is about 16.8%. Okay, so if you wanted to use a calculator, the TI-84, you can do the same thing to get this value. You would just hit second distribution, and then you would go to this binom CDF. You're going to type in your n value is 500, your p value is 0.7, and then we want x to be 29. And so we would get our area under our curve or our probability that way. Okay, let's try this one. According to the Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. Erica selects a random sample of 1,000 adults Americans in Will County, Illinois, and she finds that 630 of them are in favor of the death penalty for individuals convicted of murder. So, assuming that 65% of adult Americans in Will County are in favor of the death penalty, what is the probability of obtaining a random sample of no more than 630 adults in favor of the death penalty from this sample size of 1,000? Okay, so we have our probability. In this case, success is that they are in favor. Failure would be that they're not in favor. And just a quick reminder, the word success is just the name we give one of our probabilities. So it doesn't mean we actually agree. It just means that it's the probability of one of our two decisions, success or failure. And then we have our sample size is n. Okay, so this is a binomial experiment with n equal to 1,000, p is equal to 0.65. And so what Erica wants to do is she wants to determine the probability of obtaining a random sample where no more than 630 adults were in favor of the death penalty, and we're assuming that 65% of them are in favor. So across the country, but this is the random sample of this specific county. So computing this probability using our binomial probability formula that we've actually learned in the past, it would be pretty difficult. So instead, what you can do is you can use your normal approximation to approximate the binomial distribution, as long as this computation n times p times 1 minus p is greater than or equal to 10, which in this case it is. So we can go ahead and use our normal approximation, which is going to make this way quicker. So if we want to know the probability that x is less than or equal to 630, we compute the area under the normal curve to the left of x equals 630.5. So just adding that 0.5 right here. So our mean, we can quickly calculate that and get 650, and our standard deviation is about 15.083. And so here is our normal curve. Okay, we have our mean right here in the center. We're wanting the area under the curve to the left of 630.5. So let's go ahead and get a z-score. So this is our x value minus the mean divided by the standard deviation. So we get our z-score is negative 1.29. And using our standard normals distribution table, the area corresponding to that z-score is 0.0985. And so the probability of obtaining 630 or fewer adults in favor of the death penalty from a sample of 1,000, assuming the proportion of adults of Americans who favor the death penalty is 65%, this is 0.0985. Okay, so let me restate that. The probability of obtaining 630 that favor the death penalty out of the 1,000, 630 or fewer, is about 9.85%, given that we know in general 65% of people favor it. Okay, so then we want to know, does this result contradict the Gallup organization's findings? And so our result means that if we had 100 different simple random samples of size 1,000, we would expect 10, that was that 9.85% rounded, so about 10 to result in 630 or fewer adults favoring the death penalty, if the proportion is in fact true. So if we took 100 different samples, we found 1,000 people, but we did this 100 different times, we would expect that only out of 10 out of those 100 times, 630 or fewer would favor the death penalty. So because the results obtained are not unusual, and we'll explain why, under the assumption that p was 0.65, Erica finds that the results of her survey do not contradict those of the Gallup poll. So remember, we have to kind of go with a couple things from the past. For normal distribution, it follows the empirical rule, and then for binomial distribution, results are not unusual if they're within 2 standard deviations. And so here's your empirical rule for normal distribution. And so 2 standard deviations to the left of the mean or 2 standard deviations to the right of the mean would be considered normal. And so because this result is not outside of this range of 2 standard deviations away from the mean, that's why we can say that it's not unusual. All right, that's it. Thanks for watching.